Hi, this is Ms. Fitzmaurice, and this video is about parallel and series circuits again. This is video 2. So in this video, I'm going to recap how to find equivalent resistance. We're going to talk about analyzing the current through the circuit and analyzing voltage drops across a circuit. Okay, so just as a quick recap, we discussed this in class, but if two circuit elements are in parallel, 2 or more, it could be 17, and by in parallel we mean that they're connected at both ends. Okay, it doesn't matter what else they're connected to. So these 3 that I'm drawing right here are connected at both ends. Then the way to find equivalent resistance is that 1 over Req equals 1 over R1 plus 1 divided by R2 plus 1 divided by R3 plus ... however many resistors you have. Now if they're in series, and remember that series means that they're one after another, just like the episodes in a television series, and that if you are an electron and you go through one, then you have to go through the others, then your equivalent resistance will just be the sum of your individual resistors. So Req will be equal to R1 plus R2 plus R3 plus pretty much as many as you have. Okay, and just to make sure that you have the hang of this, I want you to try this circuit. Okay, so all of our resistors have a resistance of 10 ohms, and the voltage is 20 volts. I want you to tell me, first of all, what is the equivalent resistance? Second, what is the current through the battery? Third, what is the power? Okay, so pause this video, solve these, and check back for the answer. Okay, so now that you've gone ahead and solved these, we have to look at the circuit and we realize, first of all, that these 4 are in parallel with each other, okay, because they're connected on both ends. And what that means is that in order to calculate, I'm going to name this whole section angry face. In order to calculate angry face, we have to use 1 over R equals 1 over 10, there's 4 of them, plus 1 over 10, plus 1 over 10, plus 1 over 10, and this is our angry face. So 1/10 plus 1/10 plus 1/10 plus 1/10 is 4/10, so we have 1 divided by R angry face equals 4 over 10, and that means that when we take the reciprocal, our angry face is equal to 10 over 4, which is 2.5. Okay, so angry face altogether is 2.5 ohms. Then when we add it to our other 10 ohm resistors, okay, we see that this is in series, because if I'm an electron and I go through the first 10 ohm, then I have to go through angry face and then go through the second 10 ohm. So my total Req will be 10 plus 2.5 plus 10, which is 22.5. Now if we want the current through the battery, the current we can calculate using I equals V divided by R. So in this case we have 20 volts divided by 22.5, and we get 0.89 amps. If I want the power through the whole circuit, I can use P equals IV, and I use 0.89 times the voltage across the battery, which is 20 volts, and I end up with 17.8 watts. Okay, and now that we've solved those, I want you to try to think about these two questions, okay, relating back to the same exact circuit we had before. And I want you to think about these two questions. So is the voltage across each resistor also 20 volts? And is the current through each one of these resistors also 0.89 amps? Okay, and just write down an answer for yourself and why you think that's the case. Okay, so now that you have written down that answer for yourself, let's talk about this. And to talk about this, we need to think about what the definitions of voltage and what the definitions of current are. Okay, so voltage is, if it's the voltage something goes through, that's like a change in potential energy per charge. And if we think about current, that's the number of charges going through something per second. So, in order to answer these questions, let's think about our little electrons as they're going through our circuit. Okay, so I'm an electron. I start out at the negative end of my circuit, and I'm going around this way. And I start out with 20 volts of, or 20 joules of energy per coulomb of potential energy, but these resistors, they kind of get in my way and they slow me down. And actually, I can think about it this way: every time I go through a resistor, I lose a little bit of potential energy, and then I go through another one and I lose a little bit more potential energy. So as our electrons go around the circuit, they lose potential energy. And when we talk about a voltage drop, or what is the voltage across a resistor, we're talking about the change in potential energy per unit charge. And as we go along the circuit, around the circuit, every time we go through a resistor, it drops. And this tells us that the answer to our first question is no, because every time I go through a resistor, my voltage changing, so the voltage across each resistor is going to be different than 20 volts. If I go through the whole circuit, okay, no matter which path I take, so say I took this path instead, my total change is going to be 20, but across each resistor, it's only going to be some fraction of 20. So you lose some fraction for each resistor. Now, the second question is about current. So to think about current, I'm going to have you picture our wires instead as pipes, and instead of thinking about electrons, I want you to think about water. And if you have water flowing through a pipe, every time the pipe splits or comes back together, the flow in the water, the total flow in the water has to be constant. And that's just conservation of mass, kind of like the total current in a circuit has to be constant because of conservation of charge. And so if I had 10 gallons per minute over here, and then it split exactly into two, I would have a different current. I would have 5 gallons per minute in one pipe and 5 gallons per minute in the second, but when they came back together, I would once again have 10 gallons per minute. Okay, the exact same thing is true for circuits. If you had a circuit and you had 4 amps and it split into 2 equal parts, and this circuit over here doesn't have 2 equal parts, so we'll talk about that a little bit later, then we would expect each of our 2 equal parts to have 2 amps. So the next thing I'm going to tell you, because I kind of talked about these things, voltage and current, and how they change through complicated circuits, in a qualitative way, I'm going to show you how to actually calculate these things. Okay, so in terms of calculating voltage, I'm going to do 3 things. I'm first going to give you kind of an intuitive picture. Then I'm going to show you this method called the voltage divider method, and then finally I'm going to show you a different method for finding voltage called Kirchhoff's loop rule. Okay, so here's the first example I'm going to give you. I'm going to say that we have a certain circuit, and let's say that each resistor, okay, you should see that these are all in series, has a resistance of 100 ohms. And I know that my battery over here has 15 volts, and I want to know what is the voltage drop from A to B, what is the voltage drop from B to C, and that's like the change in potential energy per charge, and the voltage drop from C to D. Now, you might be saying, if I am an electron and I go around this circuit, then the whole voltage drop has to be 15 volts, right? I start out at 15, and then everything I go through, I lose some amount of voltage, and really I'm losing 15 volts overall. So we'd call that negative 15. And I have 3 equal resistors, so you might say to yourself, well, I might as well just divide by 3, and that is in fact the case. You know, you start out at 15, and then by the time you get down to B, you will have lost 5 volts, and at B, your voltage is equal to 10 volts. Okay, and then by the time you get to C, you will have lost another 5 volts, and your voltage will be 5 volts. And then by the time you get down to D, you will lose another 5 volts, and you get down to 0, or if you'd rather call it ground. Okay, so you just kind of lost a third of your voltage each time. So that first example was easy because all of our resistors, if you look back to it, were exactly the same, and we could probably figure out that our voltage change would be cut into equal thirds. Now, if our resistors are slightly different, you can probably guess that we're going to lose less voltage over the 100 ohm resistor than over the 200 ohm resistor and the other 200 ohm resistor. And if, again, you wanted to know the voltage drop between A, B, C, and D, you might realize, okay, well, these guys are all in series, and so my total resistance is equal to 200 plus 200 plus 200, that's 500. So, you know, 100 ohms is like a fifth of that, 200 ohms is like 2/5, and 200 ohms again is like 2/5. So maybe I could use that to figure out my voltage drops. And so you would be right. Okay, the total voltage drop is going to be 15 volts. So the total delta V is negative 15 because we're going from 15 volts down to 0 volts, and you would expect the voltage drop from A to B to be like the resistance, 1/5 of that. So the voltage drop from A to B is going to be 1/5 of the total, which is equal to negative 3 volts. And similarly, the voltage drop from B to C will be the same as the size of that resistor, and it will be 2/5 of the total, which is negative 6 volts. And the voltage drop from C to D will be, again, 2/5 of the total, or negative 6 volts. Now this intuition can be formalized in what's called the voltage divider method. And the formula for the voltage divider method is that, and so the voltage divider method says that the change in voltage across a specific element. So say you have smiley face, and smiley face is a group of resistors in your whole big circuit. And I'm drawing this messy picture to indicate that I have hundreds of parallel and series circuits. The drop, and this is my smiley face, the drop across smiley face in voltage will be equal to the total voltage, so the voltage across the battery or across the whole section you're looking at, times the resistance of your individual part that you care about, our smiley face, divided by the total resistance, or the equivalent resistance for this whole thing. So the question is, what if you wanted to know the voltage between these 3 points in your circuit? Okay, so say you wanted to know the change in voltage from A to B, or the change in voltage from B to C. Okay, so both of these cases we can use our voltage divider method. So the voltage from A to B is going to be equal to the total voltage times the resistance that's in between A and B divided by the total REQ for the circuit. Okay, so hopefully you can figure out the equivalent resistance of this circuit. Our 200s will be in parallel, so we have 1/200 plus 1/200, and we get a combination of 100 ohms. So our total REQ is 200. Okay, now if we want the voltage drop from A to B, we use the total drop of the battery, which is minus 12 volts, times the resistance from A to B, which is just our 100 ohm resistor right here, divided by the total resistance, and our total REQ is 200, so we get negative 6 volts. We can do the same thing to calculate BC. We know that the resistance from B to C is 100 ohms, and so we have minus 12 volts times 100 divided by 200, and we have negative 6 volts in total.